Okay, welcome everyone to another Let's Talk Research session. So it's my pleasure to introduce today's guest speaker, Daniel Mayfrank. Daniel is nearing the completion of his PhD at Jülich Forschungszentrum. I'm sorry if I butchered that. He is conducting his research under the supervision of Professor Alexander Mitsos in the Process Engineering Department, RWTH Aachen University. Daniel's work lies at the exciting intersection of optimal process control and reinforcement learning. Specifically, he is exploring how reinforcement learning can enhance data-driven model predictive controllers. This topic is not only at the forefront of modern engineering, but is also highly relevant to several decision-making projects and research that we're carrying out here at INSTI. We're very fortunate to have Daniel sharing his insights with us today. I'm very excited to hear him discuss his work. Please feel free to raise your hand or ask any questions throughout the talk. And with that, I will hand it over to Daniel.
Okay, yeah, hi everyone. Thanks for the introduction and more importantly, actually, for the exciting opportunity to present to you what I've been up to so far in my PhD project. And that is mainly end-to-end learning of Koopman models for control. And of course, as you said, all of this I did with the support of my supervisors, Professor Alexander Mitsos from RWTH Aachen and Dr. Manuel Dahmen from Forschungszentrum Jülich. So I know that you're all familiar with reinforcement learning, and as this talk progresses, you will probably find yourself more and more in familiar territory. However, when I started my PhD, even though I was interested in solving problems that could be classified as RL problems, having a mechanical engineering background, I didn't actually know anything about RL yet. And the tools that I was most interested in are called optimal control or model predictive control methods. And as these are central to my project, I want to give you a short introduction, even though some of you probably already know about all of this. So let's say we have a simple dynamical system with one state and one control input, and we want the state to follow some predefined trajectory. So we know the evolution of the state up until now, we know past control actions, and we know the trajectory that we aim for. So if we also have a model of the dynamics of our system, then we can set up an optimization problem to solve for the future control inputs that get us as close to the desired trajectory as possible. So we write down a cost function. In such a case, it should depend on the deviation from the reference trajectory. The equality constraints will represent the dynamics, and we can also add further inequality constraints, for example, box constraints on states or actions. And then to obtain a closed loop controller for this system, we have to solve this optimization problem. We'll get a solution for the optimal actions over the full time horizon, capital T. We implement the action only for the next upcoming time step, and then everything shifts by one time step and we repeat the process. And this approach is called model predictive control, MPC. From the perspective of an RL practitioner, MPC is basically a model-based online planning method. And it works well when we have a good model of our system. And what's nice about it is that it has quite a lot of well-established theory behind it, and that it is in principle very flexible. For example, this cost function here could also directly optimize the economics of some automated production process instead of just following a trajectory of set points. And this is then called economic MPC. And if you have a good model of your system, you do not even need to retrain anything to implement this change in the objective, since all the computation is done online. So Sutton and Bartu say that reinforcement learning is learning what to do, how to map situations to actions so as to maximize a numerical reward signal. And this definition certainly makes sense, but at the same time, in my opinion, RL also stands for a community of people who approach a certain class of problems from a common perspective. And as we can see, other communities work on very similar problems. And there is actually a lot of common ground if we can get past different terminologies. Okay, and now we can start to look at some research. Now, Let's say we want to use a model predictive control scheme to optimally control some process. For example, we might have some energy-intensive chemical production process and fluctuating electricity prices due to renewable electricity production. Now, we want to minimize our production costs by shifting production to time intervals with relatively low electricity prices. Now, even if we have an accurate mechanistic model, we might run into the problem that this process is rather complex and the mechanistic NPC therefore not real-time capable. The optimization problems that I showed to you earlier cannot be solved in real time. And here, data-driven surrogate models can help us. The idea is to approximate the mechanistic dynamic model with a computationally cheaper data-driven model so that the resulting predictive controller is then real-time capable. And as we have a mechanistic model, it's straightforward to train a good data-driven model because we can generate large amounts of high-quality training data. We can just keep increasing the amount of data and the size of the model until we end up with a model that generalizes well. However, as we increase the representational capacity of our surrogate model, so the size of the surrogate model, also the computational cost of the resulting NPC problems increase. And this again eventually causes problems regarding the real-time capability of the controller. Therefore, the fundamental goal of my PhD project was, instead of using a bigger model and more data to get better controller behavior, see if we can come up with a better algorithm than standard system identification to train a surrogate model of fixed size for optimal performance as part of NPC. So our approach to task-optimal data-driven surrogate models rests on three key methods: reinforcement learning, post-optimal sensitivity analysis, and Koopman theory. Before we get into our method, I want to briefly introduce each one of those. So this slide is just preparation, and we'll connect the dots on the next slide. Okay, I don't really need to explain reinforcement learning to this audience, but what's important is only that RL gives us the tools to train a policy for a specific task. And this goes in the right direction, but what we want is a task-optimal dynamic surrogate model that's to be embedded in an NPC policy. The next building block is sensitivity analysis. And here the idea is to differentiate the optimal solution point of an optimization problem with respect to the parameters of the optimization. For example, we could differentiate the control output of an optimal control problem with respect to the parameters of the underlying dynamic model. And in 2019, Agrawal and his co-workers released CVXPy layers, which allows the user to integrate parameterized convex optimization problems into deep learning pipelines, for example, in PyTorch. And this basically allows you to treat a parameterized convex optimization problem just like you would a normal layer in a neural network and differentiate through it completely automatically. And now Koopman theory. I don't want to go into unnecessary detail for this presentation. What's important here is that Koopman theory provides us with a data-driven approach to linearly represent the dynamics of nonlinear systems. And this linear representation of the dynamics means that we get convex optimal control problems when using these models inside an NPC, provided that the objective function and any additional inequality constraints in the NPC are also convex. Okay, so now let's put this all together to learn task-optimal dynamic surrogate models for use inside a controller. RL always needs an agent and an environment, and the environment in our case consists of the mechanistic model, which is used to compute the system response to a control input, and a reward function which provides feedback to the agent. And now to the interesting part. Instead of using a neural network to represent the policy, we use a Koopman model predictive controller. So here we can see the nonlinear transformation of an initial state into the higher dimensional Koopman space, which is followed by the convex optimal control problem. And then finally, we sample a control action based on the optimal action U star to ensure exploration in the training process. And because the Koopman models result in these convex NPC problems, we can use PyTorch and CDX layers to differentiate backwards through the NPC and learn the parameters of the Koopman model that result in the highest rewards of the NPC. And thereby we can thus learn the parameters of a data-driven nonlinear surrogate model, which do not minimize mean squared error on some given data set, but actually maximize performance on a given control task. So let's have a quick look at our case study, and then we can get right into the results. So I'm looking at an economic nonlinear NPC case study based on a model of a continuous stir tank reactor. We have two manipulated variables, the production volume and the coolant flow rate, and two controlled variables, the product concentration and the temperature, connected by two nonlinear dynamic equations. All variables have upper and lower bounds, and we can react to varying electricity prices by adjusting the coolant flow rate as we assume that to be proportional to the consumed electricity. So now the task is to train a data-driven surrogate model for those two dynamic equations, which results in optimal controller performance as part of an economic model predictive controller. And now that we're done with the theory and we know what the task at hand is, let's look at the results. So we'll compare the control performance of three different controllers in a half-year-long continuous test episode, no resetting of the environment. And as an interesting benchmark controller to compare ourselves to, we have a neural network policy trained using reinforcement learning. And then we have two Koopman NPC policies, one where the Koopman model is trained only using system identification, and one where we use reinforcement learning, and more precisely the PPO algorithm, to fine-tune this Koopman model for task optimal performance. And we'll compare the resulting electricity costs compared to steady-state production when using those two controllers, and how often a control action leads to a constraint violation. So lower is better in both columns. And now, looking at the value.
Just real quick, I think Nima has a question.
Yeah, sure.
Daniel, can you please go back? I would like a few slides where you have this mapping to, yes, here. So this psi of theta, this is also learned, right?
Yes, this is the encoder, but in the context of learning a Koopman model, the encoder can also actually make the number of dimensions larger and not smaller. So it's a bit different than a standard autoencoder network where you want to compress information. But yeah, this is the encoder part of the Koopman model.
And where does the loss of this one come in together with the loss of, I don't know, PPO or TD of Q-learning?
So basically, all parts of the Koopman model are parameterized. And these parameters are the learnable parameters of a policy. And as the Koopman model is a dynamic model, so it does not output an optimal control action. What it outputs is a prediction of your state, given the current state, and a controller. And a control input. So to obtain a policy from this Koopman model, which is a dynamic model, we need to embed this dynamic model in a model predictive controller. And that's this optimization problem that we see here. So in that way, we turn a dynamic model, which simply predicts the evolution of our system, into a policy which outputs the optimal next action based on the current state of our system. And because this optimization is automatically differentiable, we can treat this whole thing just like a neural network and train it using PPO, standard PPO.
Okay, good, thanks.
And for your information, I use the stable baselines 3 implementation of the PPO algorithm. If you maybe you know, it's
Yeah, sure. Oh, that's good. Thanks.
Yeah, no worries. Okay, any more questions?
Hiya. Yeah, I've got a question. So I appreciated the explanation on the last slide. I'm still struggling a little bit to get my head around it. So in PPO, obviously, there's a notion of actor critic. So there's like value functions that are being used as well.
Yeah.
Are those being used here, or?
Yes, I have just omitted them on the slide to not make it overly confusing. As a critic, we use a standard neural network. So this, what you see here is just the policy.
So, and sorry, just to clarify, so the Koopman model that you're training on the left-hand side, that's mapping to a space in which your state dynamics are linear. And then are you using some kind of like numerical optimization to select an action given that linear space that you're in?
Exactly.
So in a way, you're using PPO, you're treating this like predictive or this encoding model as your quote unquote agent, but that's not actually the thing that's selecting an action. All that's doing is that's embedding your states to a new space, and then you have something else that's selecting the action given that new space. And then you're kind of training.
And because all of these elements that you just described are differentiable, I can treat this entire thing as a policy. Exactly, yes.
Okay, and then you're using value functions in the same way as usual, just to guide where those gradient updates are going. Okay.
Yeah, exactly.
Okay. This is interesting. Cool. Thank you very much.
Yeah, no worries.
Sorry, Daniel, just last thing on this point, just so I can get everything clear. Can this just be thought of as like an encoder model, maybe with like an upsampling projection layer at the end to represent higher dimensionality? Or is there something specific in the architecture that makes it represented as a Koopman model? Because everything, my understanding, is trained end to end by the reward. So is this just a framing, or I guess is there something specific that needs to happen?
Okay, so the cool thing about the Koopman architecture is that it gives us this way of modeling a nonlinear system in a way that so that we end up with a convex optimal control problem. And so the Koopman model is not only this encoder here. So this encoder that we see here is part of the Koopman model, but the entire Koopman model also has this linear prediction module and also a nonlinear, a linear decoder, which maps back to the original space. And so these are not visible in this figure, as well as the encoder is visible, but these are basically these A, B, and C matrices that we see here. So psi, the encoder, is parameterized by theta, but theta also parameterizes these 3 matrices here, which are also part of the Koopman model. So
sorry, the A and B matrices, are they like analogous to like the A and B matrices in selective state machines, or is it a similar idea for predicting the dynamics?
Yes. I'm not sure about the selecting state machines because I don't know.
Sorry, not selective, just the standard state space models.
Yeah. Just yes, exactly similar. The difference is just that they operate in the lifted space of the Koopman space, where the dynamics are approximately linear, basically.
Gotcha. Awesome. Thank you.
Yeah.
I guess one more question, Nico.
Yes. So in this part, you only train the encoder in the policy. Do you have a separate step where you train the decoder of the Koopman model? Because you say you need these other matrices as well, which are also part of the Koopman model. But yeah, do you train them separately, or do you get the gradients just from deriving the optimization process?
It's all trained at once. If this was a big neural network with several layers, then you would also have parameters for each of the layers. You'd still be able to train them all at once, and we're doing just the same. We're viewing the entire thing as a policy and updating all the parameters at once.
Does that mean that there's almost like going to be an aggregate loss function where there's a loss for kind of consistency of the encoder-decoder architecture, and there's also an additional loss for the...
That's the pre-training part based on system identification, where yes, you have, when you train a Koopman model, you do not only train for minimum prediction error, but you also train for consistency with regarding the encoding and the decoding. But that we only do in the pre-training part, which is the system identification part. And then when we go this second step, where we take the pre-trained model and we refine it using reinforcement learning, we don't impose any additional loss terms. We only use standard PPO.
Right. So yeah, going back to what Nico was asking, I guess, because the parameters of the decoder are appearing in this internal linear model that you're then optimizing, those parameters will be getting updated by the loss, the PPO loss, because they're included in the decision making.
Yes.
Yeah. Okay. Cool. That makes sense. Cool.
Yeah.
Thank you.
Yeah.
I think that's it for questions now.
Okay. Cool. Yeah. Then yeah, let's have a look at the results. As I said, we compare electricity costs when using these controllers compared to steady state production, and how often control actions lead to constraint violations. So when we look at the results, we can see that the Koopman system identification controller achieves the highest cost savings. However, it does so while violating constraints rather often. And fine-tuning this Koopman model using RL drastically reduced the number of constraint violations. However, cost savings also dropped by about 40%. And the neural network benchmark achieves nice overall performance with relatively high cost savings and also few constraint violations. So even though these results maybe look promising, the difference in the economic savings is quite big. And when we looked at the learning curves of the Koopman RL training runs, we also saw that convergence to high rewards was pretty unstable. So we started thinking about how we could further improve the learning process. And
sorry, Daniel, before we move on, do you have any intuition on what a pure RL solution would, or system would achieve compared to the Koopman RL? Like if you just put vanilla PPO into this, do you have any intuition on how that would behave in comparison?
yes, that is exactly this NLP.
Apologies. Okay.
That's exactly this one. Yeah. And
sorry.
Yeah. So we see that we're worse until now. So this is why now let's have a look at what we can maybe still improve.
Sorry, one more question from Nico.
Yeah.
Did you compare the Koopman models of the system identification versus the RL? Like, what were the main changes? Like,
yes, we did. I mean, these are details that I don't have in the presentation right now. You can find them in the paper. Basically, to sum up, what we saw here was that the encoder and the decoder were mostly affected, by this end-to-end training using reinforcement learning, and it basically made the autoencoder part of the Koopman model more conservative in a way, so that it mapped states that were near a bound. When you map them back and forth from the original state space to the Koopman space and back, it more often than originally mapped them towards the outside of the feasible space. So this results in a model that predicts that the states go towards or beyond the bounds, and therefore the decisions that the resulting controller takes will be more conservative, which I mean also makes sense when we look at these results, in that savings go down, but we also have far fewer constraint violations. Does that make sense?
Yes, thank you. That makes sense.
Yeah.
Also, the smoothing makes sense along the, like, you don't have data out of bounds. So
yeah. But yeah, I mean, we have a small section on exactly this question in the paper. So yeah, you can have a look. Okay, should I continue?
Yes, please. Thank you.
Okay. So we started thinking on how we could further improve on this. So, and one thing that is usually really cool about RL is that all the methods are designed to enable learning with real-world physical systems, right? And the classic example here is that of some robot learning to walk in the real world. But at the same time, this also means that standard RL algorithms view their environment as a black box, a pure input-output system plus a reward. And RL algorithms therefore really just do an approximation of policy gradients in order to improve the policy. And it has been shown that these approximations can get rather inaccurate near the optimum. Now, when we train our policy using a simulated environment, then the dynamics and the rewards might be differentiable. And in our case, where we want to train a surrogate model for a mechanistic model, the environment is always simulated, and so it makes sense to think about whether we can leverage this in our policy optimization. Now, when all three elements, which you can see here, the transition function, that's the simulation model of the system, the policy, and the reward function, when these three are automatically differentiable, it's really easy to write a very naive policy optimization algorithm. You could just take the current policy, run it for a full episode, so capital H steps, you sum up all the rewards, and then you can simply use something like PyTorch to do an optimization step with respect to the policy parameters, and you repeat the process. Now, sadly, as some of you may know, this backpropagation through time approach does not work very well in practice, because the concatenation of many time steps in an episode leads to vanishing or exploding gradients and an optimization landscape with many local minima in which the optimization can easily get stuck. However, a research group at NVIDIA addressed exactly this problem in 2022 with the short horizon actor critic algorithm, SHAC. And the key idea is to avoid the problems of backpropagation through time by dividing each episode into multiple short sub-episodes. And in order to still be able to learn a far-sighted policy that isn't too greedy, you learn a value function simultaneously to the policy. And this value function is used to estimate the rewards to go, starting from the last state of each sub-episode. So now, instead of sampling a full episode at once, we only do a short sub-episode, and then we do an optimization step to maximize the sum of rewards plus the estimated value of the last state. And then we continue with the next sub-episode. So SHAC introduces a few more tricks, but this is the basic idea. And SHAC outperforms normal RL algorithms on various tasks when training neural network policies. And just like we previously used the RL algorithm PPO, we now inserted our differentiable Koopman NPC policy into the SHAC algorithm. So now we can use SHAC not to learn a neural network policy, but to train a task optimal dynamic model for control. And then we tested this same case study as in the initial end-to-end Koopman NPC project. To be able to use SHAC for training, I had to slightly tweak the reward function in order to make it differentiable. But I mean, this is not a big problem, so we can have a look at the results.
Sorry, Daniel, do you mind if I just jump in with a quick question? Could you go back to the last slide, please? Here is the idea that you're making decisions online and receiving updates from the environment, or you're just using your model to do full rollouts? You have like a pre-trained differentiable model and you're just doing rollouts through that and doing updates. What's the...
Yeah, yes, exactly. So this only works if you have a simulation model. But I mean, in my research question, where I mean the idea is we have a mechanistic model, but this mechanistic model is too computationally expensive to be embedded in a real-time capable controller. So we want to find a computationally cheaper approximation to that model. And that's why in my specific problem setting, it makes sense to try to leverage the differentiability of a simulator in policy optimization. Of course, this is not generally applicable in the general RL setting.
So just to clarify, I think when you showed the last example with the Koopman model, we'll be doing like online learning, whereas this is, so that was like making a decision, applying it to the environment, receiving a reward, and doing updates kind of with PPO, whereas this is, you actually train your model offline and then you're using that model to do RL training afterwards with like a pre-trained simulator. Is that correct, or am I misunderstanding? Sorry. Here is the model fixed, or is the model updating?
I guess if I'm not mistaken, it's analogous to the likes of mu0, where you are at the same time you are learning your policy as well as a latent dynamics model that you can use throughout.
Okay, sorry. Yeah, I thought here the rollouts were happening just under the model, like with no environment interaction. Yeah, okay. Cool.
Yeah.
Sweet, thank you.
Okay. So I'll continue, yeah?
Yeah.
Yeah. So yeah, we can look at the results now with SHAC, and the new reward function, which is now differentiable, leads to PPO reducing the average size of constraint violations, but small violations still occur almost as often as before the end-to-end refinement. But SHAC, however, this time gives us really nice results with high savings and no remaining constraint violations. And the results of SHAC with a pure neural network policy are also quite nice, and it uses the exact same reward function. So even though this is just a very small case study, these results indicate that the advantages of using differentiable simulation for policy training also apply to the end-to-end learning of dynamic models. And future research should investigate this further on larger and more realistic case studies. Still, so far, I haven't really given you any arguments as to why you shouldn't just learn a neural network policy, like the vanilla version, as you called it, instead of going for the NPC. And of course, both variants have their pros and cons. For starters, it very much depends on your specific problem, whether learning a good dynamic model or a good policy is easier. For example, on this CSTR problem, I personally found that the training of the neural network policies was usually much easier and faster, actually. On the other hand, some people argue that NPCs are more interpretable than neural network policies, and therefore might be safer and all in all preferable. And I would like to show you another reason for why learning an NPC policy through RL can sometimes offer concrete advantages compared to learning a neural network policy. So one standard problem that neural network controllers struggle with is adapting in case of a change to the environment after training has completed. And obviously, there is a big difference between NPC controllers and neural network controllers in that the NPC controllers have explicit representations of a cost function and constraints, and these therefore can be changed after training has completed. And as long as the dynamic model generalizes relatively well, the new NPC policy will still work well without requiring any retraining. Neural network policies, on the other hand, simply learn the reward structure during training, and they do not have an explicit notion of constraints or an objective function, and therefore cannot adapt if these change. So on this slide, I want to show you that reinforcement learning, a dynamic surrogate model, retains this inherent adaptability of NPC. So after doing all the training, we reran the tests with shifted bounds for the concentration variable and checked whether the control output adapts in a sensible manner. And these are the results that we generated before we tried out the Shack algorithm, so that's why we don't see the Shack variant up here. As we can see, for example, if we tighten the bounds, as can be seen here on the left, then the Koopman RL controller keeps the concentration variable within those new bounds, whereas the MLP controller still uses the full feasible range it had during training, which makes sense because it cannot adapt as it simply does not have a notion of constraints. Now, same goes if we widen the feasible region or we completely shift it to somewhere else. If we relax the bounds, of course, the neural network controller does not fail catastrophically, but then again, it also does not utilize the increased potential for flexibility in this scenario. So to sum up, I think that this is something that would be worth looking closer into, the pros and cons of both methods. But one advantage of the NPC approach is that I would say stuff that is learned implicitly by a neural network policy is explicit in an NPC and therefore can be changed whenever you want to.
We have a question from Nico.
Yes, did you try embedding the bounds to the MLP, like telling it what the bounds are?
No, we didn't, and this of course makes sense, but if you want to do that, then of course you would need to know a priori what possible changes could be. And I would say the whole argument is a change comes up that you haven't foreseen, but you simply change the code a little bit in a very easy way, and your policy functions again. You do not need to know a priori what the different scenarios could be.
And I have a second question, which is a little bit unrelated, like more general. So am I correct in assuming that this Koopman model is Lyapunov differentiable, that you can find, like prove this to be Lyapunov stable?
There is research on that. To be honest, I am not completely sure about that, and I think it depends because there are different variants of this Koopman modeling framework, and I use the one by Korda and Mesic, which was published in 2018, and I'm not, to be honest, I'm not exactly sure about that.
Okay, just for the case it is possible, you could probably have done a significant contribution to the field of safe reinforcement learning there. Because if it is, then you could bound your PPO in such a way that it would never actually try any non-Lyapunov stable functions. You have this clip notion in PPO, which is an attempt to do second order optimization without doing second order optimization. And instead of that, you could clip at the Lyapunov bounds and automatically go along that way. It's just an idea, though.
Yeah, that sounds very interesting. Yeah, thank you. That I will look into that.
Cool. I think we can keep going.
Okay, cool. Yeah, now we actually change a little bit. We're getting to the last part of this presentation and a small glimpse into a project where we're working on at the moment, and where we want to address a slightly different issue. So even though RL has had quite a few impressive success stories in recent years, it is still not used that much in the process control industry. And the main reason for that is the poor sample efficiency of RL methods. For example, when running PPO using a neural network policy on my little CSTR toy problem, it takes around 100,000 simulated hours of training to get a half decent policy, and much more than that for really good performance. And yeah, as you will know, this makes RL a bit painful to work with in silico, and it's often a complete deal breaker when talking about real world physical systems. But of course, there are ways to address exactly this issue. For example, the field of model-based RL and the family of algorithms that are based on the DINA algorithm. And the basic idea here is to let the policy interact with the environment just like in normal model-free RL, but then we collect all the experiences in a database and use it to learn a dynamic model of our environment. And then in a third step, we can use the learned model to train the policy using standard model-free RL, and thereby strongly reduce the number of interactions that are needed with the real environment. So basically, we want to substitute these costly interactions in the real world with these cheap interactions with a learned dynamic model. And the main challenge in this approach is that we are trying to learn this dynamic model with as little data as possible because we want to maximize sample efficiency. So this model will not be perfect, and the agent will probably learn to exploit the errors of the model, leading to high simulated rewards, but a policy that fails in the real environment. So now there are different ways to counteract exactly this challenge based on learning ensembles of dynamic models. And together with a colleague of mine, Mehmet Veglioglu, we are also experimenting with physics-informed neural networks to include some prior knowledge about the dynamics. And I think we're getting quite promising preliminary results. So this here is the learning curve of the neural network policy trained using PPO on the CSTR demand response case study. And this here, and please mind the very different x-axis scaling, are learning curves of neural network policies trained in the same environment using model-based RL. And the variant depicted in blue also uses physics-informed model learning. And this seems to also contribute to the sample efficiency. And then lastly, of course, we also tried this for our Koopman eNMPC policies. And in the yellow variant, I actually only did system identification of the Koopman models, so only MSE minimization with respect to the data that the policy had acquired from the environment. So actually no reinforcement learning going on, just system identification with a data set that grows successively. This could also be called adaptive NPC. And then we can see the model-based RL variants in blue and in green. And we can see that they actually learn quicker than the pure system identification variant, which is probably due to the ensemble of models that we learn in parallel to the Koopman model here. And again, the PINs, the physics-informed neural networks, also seem to do their part in increasing overall sample efficiency. But yeah, as I said, these are preliminary results, and we'll have to wait a few more weeks until the final results are out. Yeah, and with that, I'd like to thank you for your attention until now. And I would also like to thank HDS Lee, the Helmholtz School for Data Science in Life, Earth, and Energy, for funding me. Yeah, and now if you have any remaining questions, of course, I'll also be happy to try to answer them.
Awesome. Thank you so much, Daniel. It was an excellent talk. I'm sure there'll be more questions. Just to kick things off, I guess, what is your intuition on how well these methods scale to more advanced problems in comparison to other RL or even control-based methods?
I do not have a clear intuition on this, but we will check this now. So I have a master's student starting. He started last week for a thesis, and he will try to apply these end-to-end learning methods for the Koopman eNMPCs to a much bigger problem. It's a model of an air separation unit with around 500 differential states and over 2,000 algebraic states. So yeah, there we will see how well all of this scales. I'm very excited and a bit nervous for that, but yeah, more excited.
One more question on my side before I hand it over. We've seen before that when we kind of put in like a dynamics model or a encoder model and train it end to end, that a lot of the policy, decision making within the policy is also embedded into the encoder, and when you separate them out, the policy significantly drops. Do you see something similar when you're training the Koopman RL models end to end, or do you have any intuition of how much it is kind of differentiating between learning the Koopman model and how much it is between the RL policy?
I'm not entirely sure that I got your question correctly. There are in the policy, apart from the parameters of the Koopman model, there are no other trainable parameters.
So I guess to make the question more concrete, what I've seen before is that what we thought was coming from the encoder, and that the encoder was producing a sensible latent representation of the environment. When we kind of discovered how the parameters were being used, really what was happening is it was just giving more capacity to the actual PPO algorithm. And when we just increased the depth and capacity of a standard PPO algorithm, that it performed just as well. And I'm wondering if there was ever any like analysis into like where I guess the performance was coming from.
No, I'm not sure about that. I would say that in the problems, like in this problem that we've looked at so far, both variants give us really good performance. So, I mean, basically, we show that you can also go for the MPC if you want to do RL instead of using a neural network policy, but both variants work. That's why, so in my opinion, this whole thing becomes interesting if you want to do MPC for some reason, but you also want to get the advantages of end-to-end learning for a specific task. If you're fully fine with having a neural network policy, then, I mean, maybe then you would actually have to look towards these safety things to find, or what I alluded to earlier with the adaptability to different scenarios that you hadn't foreseen in the training, where advantages of an MPC could come through.
Awesome, thank you. Yep, Nico.
So first, yes, from my background in wind turbine industry, proving Lyapunov stability is one of the constraints for quite some industrial controllers. So if that is possible, that's a lot better. I know that for some MPC tasks, you can distill out a PID from the MPC. Is this also possible in this case? Have you tried how close it is to the MPC performance?
In my from my knowledge, this is possible under certain circumstances which are not given in our case study. So if we wanted to do set point tracking without hard constraints on the states, so just following a set point, minimizing the distance to the set point, then we could distill out a linear quadratic regulator policy in the Koopman space. And then we wouldn't have to solve an optimization problem online anymore as part of the policy. That is possible. I've also tried that and it worked. But this is, from what I know, constrained to certain types of an objective. So basically to certain shapes of the NPC optimization problem. Does that make sense?
Yeah, I guess it does. Maybe you could hack in your constraints as costs then, but it's not as nice for sure.
I'm not sure that you could actually do that, because the constraints should be zero, like the inequality box constraints of a variable should be zero across the entire range of the feasible space, and they should only become non-zero when you leave the feasible space. And from what I know, the constraints that you have in an LQR controller are non-zero only at a certain point. That not correct?
I'm not super familiar with LQR constraints, to be honest. I was just assuming that you could make a linear constraint which is close enough to zero so it doesn't hurt you, but this is fast enough at the boundaries that it actually acts like a constraint. Like that's what I meant with hack.
Yeah, it could be. It could be. I haven't looked into it, to be honest.
Nima, you have a question?
Yes, I have two questions. One of them is about this ensemble reinforcement learning and different models that you have. Can you briefly comment on how do you combine different models? In which
Yes.
do you do the ensembling?
Yes, of course. If you want all the details, I would recommend this paper, because this is the algorithm that we follow, this model-based policy optimization algorithm. But to get you the main idea is that we learn multiple models in parallel from the experience, and the way in which these models are or become different from one another is that we use different random initialization at the beginning, and we also do the mini batching during the model learning randomly and differently for each model. So this is how they sort of learn to represent the same data, but there where they don't get the data because this is limited, they sort of get different errors which counteract each other. And then in the RL part, we embed all of these models into the environment. And with each step that the policy takes in the environment, we sample randomly one of the models and use this model to represent the dynamics of the system. So we don't average over the models, because then we would end up with one model again with certain errors, right? We actually force the agent to sort of be able to deal with any of the models by sampling one of them at random at each step.
Good, thanks. That's very interesting. And thanks for the reference.
Yeah, of course.
Another question, back to what Donald was discussing with you. So if this is the case that you only have your learnable parameters are only in this Koopman decomposition, then that should be definitely a function of the reward, right? If you change your reward, that should change. So basically your dynamic, I mean, the composition of your dynamic depends very much on the reward.
Yes, yes.
Have you looked into it that it would really show that there is a big difference between it if you change the reward and all of a sudden the way that you can decompose into your dynamic into a linear, basically map it to a linear space would change?
I mean, in my opinion, this question goes a little bit into the same direction as the question that we had before on how this end-to-end learning process affected the model compared to the variant which was pre-trained only by system identification. And I mean, there we saw that the way in which the Koopman model was affected was very intuitive, in my opinion, in that it made the model more conservative towards the bounds of the system. So, and because this change in the model was in a very intuitive way, I would also assume that if we train for a completely different task with a different objective, then we would also see sort of intuitive changes to the model. For example, if we were to train the model to stabilize the system around a certain set point, and this is always the same set point, but we give some random perturbation to the system so that we always jump a little away from this set point, but then the task of the NPC is to stabilize the system back towards that set point. Now, if these perturbations are rather small and we are always in a rather narrow region around the set point, then my intuition would be that this end-to-end refinement of the dynamic model would make the model more accurate in this narrow band where we are now always in, and maybe would weight data points outside of this narrow region as less important, basically. I hope this makes sense.
Oh, it does, it does, it does.
Yeah, but we only, to make it clear, we only studied this for the eNMPC case.
Yeah.
Like this second part of my explanation was just my intuition.
Thank you.
Yeah.
Okay, I think we're going to cut it there because we're just over time. Dan, once again, thank you so much for coming in and delivering such a great and compelling talk. It was super interesting. Thanks everyone for attending and the great questions. And shout out to Nima for again helping organize this and making this possible. Guys, this is part of the Let's Talk Research kind of series that we have been doing. We'll be publishing this on our YouTube channel, and we're keen to get more amazing guests like Daniel out there. So please, when it does go live, please share it, subscribe to it. And also, if there's any other guests that you think would be excited to come share their work with us, please don't hesitate to reach out. Thanks a lot, guys.
Thank you very much. Bye-bye.